So we want to think through this thing. So going to the other state is spontaneous. Spontaneous is the same thing as saying delta G minus. Usually minus is a bad thing. In this case, delta G minus is a good thing. So if your delta G, if your G, your free energy is decreasing as you let the air out of your soda, then the line has to be higher or lower. Lower, you're going down. Right. So you know that this has got to be down here. If my pen would write. Why is my pen not writing? There we go. Oops. Why is it? CO2 in air. All right. The other thing we know is that there's got to be some transition state. And there's a reaction path. Goes through this transition state. Well, that's why it was misbehaving. All right. And the transition state, it turns out in this case, is tiny carbon dioxide bubbles are easily crushed by surrounding water. That's the same thing as saying there's a high activation energy. Therefore, few molecules with energy greater than EA, therefore slow rate. Okay? So it turns out it's actually got to do with sort of size and scale and geometry, that basically the itty-bitty bubbles face a significant pressure. So how does this carbon dioxide get out of the water? Well, this carbon dioxide molecule is dissolved among the water molecules like this, right? Sprinkled in among the crowd of water molecules. If a couple of carbon dioxide molecules happen to collide together in the same place, you get effectively an itty-bitty little carbon dioxide bubble, a little crowd of carbon dioxide surrounded by water. Turns out the water molecules typically gang up and, because of surface tension and a variety of things, squish that bubble out of existence and the carbon dioxide goes back into solution. The only way you can get a serious bubble that's then going to graduate and float out of the tank of water is if you get a lot of carbon dioxide molecules all together at the same time. Then they can build up a significant enough pressure to withstand the water, and then they're of decent size, and more carbon dioxide can come in and the bubble can come out. So it turns out those tiny bubbles are a rate-limiting step. And so that's why it takes so long. Forming those little bubbles is what holds you back from getting the gas out of the out of the soda. Yeah. So with energy greater than the activation energy. So the idea is there's not enough, because you've got to hit hard enough to form that little bubble, and there's not enough, at room temperature, there's not enough energy in those guys to collide and have that happen. Right? So the thing is, there's a couple notes about this. This is a reversible process. That is, can put fizz in soda, but requires energy input. That is pressure. Got to squeeze it in. All right. So if you wanted to make your soda go flat sooner, I don't know why you would, but say that you did, to increase the rate, you could either heat it up, and that is you increase the average energy, right? Or add a catalyst. That is, and you lower the activation energy. So while people are writing those down, I want to show you a little bit of video of a demo, because if it actually, this turns out to be a fairly messy demo to do in practice, so I made videos of it. But it turns out you can see these effects yourself. Right? Simplest one is if you keep your soda cold, it stays fizzier longer. But it also turns out if you heat it up, it will go flat faster. So let me show you some little clips of video I made. So this is, all right, so uncatalyzed. So this is your standard soda. And what you see is it's sitting in a beaker, and the bubbles are coming out, and it's relatively slow. One of the interesting things is most of the bubbles actually seem to be starting down at the bottom, which I can explain at the end. But it's bubbling relatively slowly. All right? That's your sort of standard soda at room temperature. Right? If I instead talk about, you could increase, so so the problem is, oops, I'm sorry. Here we go. What's going on here is you can't see, in the water, there are zillions of itty-bitty bubbles forming and getting crushed, forming and getting crushed, forming and crushed. Only every once in a while do they form big enough to get strong enough to survive the water pressure and graduate and actually float to the surface. So that's why this is happening rather slowly. All right. So we can heat it, if you like. And so what I did here is I took the soda thing, and I put one of those little teacup heaters that can heat up the water in a teacup. At the moment, it's turned off. And you'll see in a second when I turn the heat on. So it's still bubbling slowly, okay? And in a second, the heat gets turned on. Again, it's the same thing, bubbles forming, getting crushed, etc. So it's going rather slowly. At some point, I'll turn the heat on. I forget exactly how long I waited. There's a certain amount of patience. Any second now. Oh, hum. All right. I maybe made that scene go on a little long. All right. There we go. The heat's on. And this is not boiling. This thing is just getting warm. It's not how it just turned on, so it's not actually hot enough to boil. You see a much more vigorous reaction happening here. And it's right where the water is warm. So what's happening there? The molecules are jiggling around a lot faster because I've heated them up. And the result, they're colliding more often. So more collisions, more chance of a lot of them colliding, more chance of a big bubble forming. You get this thing going. So you can heat up your soda and increase the rate at which it goes flat, which is rather... which is one way to do it. Again, it's not an option available to living things. Catalyst, however, you can also add a catalyst. What a catalyst be in this case? Something that makes it easier for those itty-bitty bubbles to form. And it turns out, so I learned this trick from my high school girlfriend's dad. For some reason, loved to have his beer flat. So he would dump sugar in his beer, not stir it up, just the powdered sugar into his beer like that, and you get this incredible fizzing reaction. Right? And the beer goes flat in a hurry. Why you want flat beer is entirely beyond me, but in any case, that was his thing. Your soda goes flat really fast, right? I mean, significantly faster than heating it. This is still at room temperature. That fizz is almost all gone by now, right? And you can see little bubbles coming up off of the sugar. All right, so and it's not that the sugar dissolved. It's not a chemical reaction. Let me show you this again. So again, it's sitting there doing its thing, not doing much. If you dump in some sugar, you get a dramatic increase in the rate, all right? And so there, we haven't heated it up. We haven't made the molecules have more energy. We've lowered the bar. We made it easier for bubbles to form. So there's more chance a bubble will form. So more bubbles form. You get more bubbles. The thing goes flat faster. Okay, so the choice is if you want to get over the bar, you can jump higher. That's like adding heat. Or you can lower the bar. And so what the sugar does is lower the bar. In a second, I want to tell you how sugar lowers the bar. But before I go there, I want to make sure everybody's with me on what we're demonstrating here. We're talking about how it works. All right. So it turns out the way sugar works is a lot like Diet Coke and Mentos, it turns out. It's actually a physical reaction. So how does sugar catalyze state 1 going to state 2? It turns out that sugar grains, if you look at them under the microscope, have lots of cracks and holes on the surface. Lots of nooks and crannies. And bubbles that form in the cracks have sugar for support. Therefore, easier to form tiny bubbles. That's the same as lower activation energy. Therefore, more molecules have enough energy. That means a faster reaction. The note here is this is a physical catalyst, not a chemical. All right? So what's happening is, again, those little bubbles forming, get crushed, forming, get crushed, forming, get crushed. But if they happen by chance to form up against the sugar, one of those canyons and cracks and crannies in the sugar grain, then they've got some support. Like if it forms up against me, it's got me to support it, right? So it's got some extra strength. So activation energy is lower. Those little bubbles are stabilized. You get more of them, faster reaction. That's also why you tend to see along the cracks, like when you didn't have the catalyzed reaction. If you looked at the bottom of the beaker, and we have you see in a glass, if there's a scratch in the glass, you'll see bubbles forming on that scratch in the glass. Why is that? That scratch is a great big old canyon from a molecular point of view. The edges of that canyon stabilize the formation of those bubbles. It gives them a couple of free sides, if you like. So they only have to form a few sides, and they get started off better. So that, in general, it's a physical catalyst like that. The other thing about this is it's like this classic Diet Coke and Mentos. You throw Mentos in Diet Coke, and you get this sort of volcano of Diet Coke. The interesting experiment that tries, if you try that with Mentos that you've had in your mouth for a little while, it doesn't work. And the reason is, it's not the chemistry of the Mentos, it's the surface of the Mentos tablet thing. It has lots of little nooks and crannies in it, tons of them. So it catalyzes the formation of these little itty bitty bubbles. But if you hold it in your mouth for a while, you dissolve off that coating, you smooth off all of those little nooks and crannies, and it won't work anymore. I haven't actually tried that, but that's what people tell me. Questions about this, how it relates to catalysis? I'm going to take it a step further in a minute, but I just want to make sure everybody's with me on what I'm talking about catalyzing, reducing energy, that kind of thing. Yeah, Sabrina. Define a catalyst is something that reduces the activation energy. So it makes it easier for the reaction to happen. If you want to put it in a very simplistic way, the more technical way is it reduces the activation energy so that more molecules have enough energy to react. Okay. Yeah. So this is a weird catalyst. It's a physical one. So in fact, strictly speaking, anything grainy like salt or sand should also do the same thing. I've never tried it, but presumably it should be the same. There are chemical catalysts, I think, that could do this, although I'm not sure. But a chemical catalyst would actually get involved in a chemical reaction. This one's actually more of a physical thing because it's like supporting the bubbles. Yeah. So what happens when you shake soda? My guess is you're actually forming little itty bitty air bubbles. So you're starting off, you're getting a big head start. So when you shake it, so theoretically, if you shook a bottle of soda that had no airspace at the top, it shouldn't matter. But if you shake up a bottle of soda that's got some airspace, you're going to trap some little bubbles in the soda, and those are started off already, so it gives them a head start. So you can't say, that's not really a catalyst, that's even a different thing, but there's no word for it in this language here, but that's what's happening. Right. All right. So let me say a little bit more about these things in general. So catalysts in general. Right? Number one, they increase the rate by changing the reaction pathway. So instead, in the case of the sugar, instead of having to form these naked bubbles in the very cold and unforgiving world of water squishing them down, you get to form the bubbles in these little nurseries on the sugar grains. Right? So you're still forming little bubbles. You still got to go from carbon dioxide in the water, little bubbles, big bubbles. But you're just making it easier. You're making a slightly different path. You're sort of propping up those little bubbles. So you're changing the pathway, which leads to a reduction. So you reduce activation energy, so more molecules have enough energy to react. And that gives you a faster rate. A couple things. They can't make delta G positive reactions happen. In this case, example, so adding sugar to flat soda won't bring the fizz back. So catalysts are not magic. Right? If a reaction is not going to happen, if its reaction is delta G positive, catalyst only makes things worse, right? It actually, in fact, increases the rate of the back reaction. The more important thing is it can't make the forward reaction happen. Catalyst can only help you if the reaction is going to happen anyway. So like if I can't think of a particular one, but there might be some catalyst that would turn your diamonds into graphite faster. But that catalyst can never switch graphite back to diamond. Right? It can make the delta G negative reaction happen faster, but it can never make a delta G positive reaction happen. So it just affects the rate, not the overall reaction. Number 3 is they're not altered by the reaction. They can be used over and over again. That is, an individual sugar grain can form a bubble, it comes off, form another bubble, it comes off. In practice, the analogy breaks down a little bit because the sugar is going to start to dissolve, but until that happens, the sugar grains can be used over and over and over and over. Levi? Are there catalysts that make delta G reaction positive reaction happens? No, it's thermodynamically impossible. You cannot go energetically uphill. You cannot go from unstable to stable. I'm sorry, from stable to unstable without putting energy in. So a catalyst can't help you. Only for delta G negative reactions. They're not altered by the reaction. And the last thing is that they are typically reaction specific. That is, sugar won't catalyze all reactions. There's no such thing as sort of a generic catalyst that makes any reaction, any delta G minus reaction happen. They're typically, because they have to help at the transition state, they're specific for specific reactions. Certain catalysts help certain reactions and not others. And the last thing is that they are a better option for speeding reactions in living things than heat. Right? You can always make a chemical reaction go faster by heating it. So I want to digest my lunch, as I said, I can put it in a pressure cooker, I can put it in the oven, it starts to break down. Right? Problem is, that's no use for a living thing because they have to operate within a narrow range of temperature. So if I want to digest my lunch in a hurry, I need to do it by having catalysts, which we'll talk about next time, which are enzymes, which are molecules that increase the rate of reaction. All right, so last questions before we do the clicker. Very well, let's do the clicker and we will call it a day. Get rid of that.